first law of thermodynamics, that the easiest way to remember that is energy is not created or destroyed, that the energy of the universe is constant, or the change in energy equals zero. These are all different ways we state the first law of thermodynamics. We are going to revisit delta H, or enthalpy. You had that last semester in Chem 105, but I think we need a refresher on it before we talk about Gibbs free energy, which will be an upcoming lecture. So I just want to kind of quickly go through delta H again. I'm not going to spend a lot of time with it, but you do have the PowerPoint, and let's say I don't remember anything about enthalpy from last semester. You can always look at the PowerPoint later and go through those slides to say, oh yeah, now I remember it. So the focus of this chapter is spontaneity, entropy, second law of thermodynamics, and then we'll get to the third law of thermodynamics. That's what the focus is going to be, and then Gibbs free energy. All right, so this is the first law of thermodynamics in equation form. So U stands for internal energy. You may not like the symbol U. Maybe you're used to a capital E, and that is fine too. So you can use U or E here. The physics, people who major in physics or physics professors, they generally like to use the capital U for internal energy. So what this is saying is the change in the internal energy of the system plus the change in the internal energy of the surroundings must equal zero. So what that is saying is that we know that the system and the surroundings make up the universe, and so the change in energy of the universe is equal to zero. And that is the first law of thermodynamics. What this is saying is that if the system gives off heat to the surroundings, then the surroundings absorbs that heat. So think about it this way. When we talked about delta H, enthalpy in Chem 105, we said that if the delta H is negative, it's an exothermic process. And so let's say for delta U, the system, I have negative 5 kilojoules per mole. Well, when we plug that over here, we get positive 5 kilojoules per mole. So whatever energy was lost by the system, which is signified by a negative sign, that is the energy gained by the surroundings, which is signified by a positive sign. So negative means release of energy from that, whatever you're focused on, and a positive value means absorbed. And just remember that change in anything, the delta symbol represents change. It's always final minus initial. Always final minus initial. The other thing is this. I can't tell you exactly how much energy is in this pen. So we don't know how much energy is in the pen. So we never know what U is because we're in the universe. All I can do is measure changes in energy. So I can burn the pen and determine how much heat is given off by the pen. So everything that we're going to be talking about here is going to be changes in energy. So U itself, or energy itself, by itself is going to be pretty much a theoretical point because we're inside the box. We're inside the universe. So energy is the ability to do work. The types of work we're going to focus on is heat and pressure volume changes. And so this is, again, back from Chem 105. So this is not in your book for 16. This is something we're going back to 105 just to kind of knock out enthalpy again. So what is work and heat? All right. So the change in energy, internal energy, is equal to heat, which is Q. And we've seen Q before when we were calculating the amount of heat required to raise 25 grams of water from 20 degrees Celsius to steam at 120 degrees Celsius. We've calculated Q already. We use Q equals specific heat times mass times change in temperature. We haven't talked about work that much, but we did talk about it at 105. But work, the type of work we're interested in chemists is pressure volume work. So let me write that down just to kind of give us a refresher on that. Turn on the dot cam here and put it in the middle. So the type of work that we're going to focus on in chemistry is work equals negative P delta V. Work is equal to negative, it's not showing up too, there it is. Work equals negative P delta V. All right, so we'll show a picture of how that equation plays out here in a second, but those are the two things we're going to be focused on when we're looking at changes in a chemical reaction. Now, something to keep in mind, work or energy is a state function, and just a refresher of what a state function is, it is pathway independent, So, just again, what a state function is what is the state of that, it is what is the position of something at that particular time of measurement. So let's think about it this way. I could climb up the stairs here and I would be higher at the back of the room than at the front of the room. And I could make that route directly up, just right up the stairs, or I could circulate back and forth between the rows, but I eventually get to the same point in the back of the room. And if I fell from the back of the room back to the floor here, it would be the same amount of energy. So energy is a state function, and that's just, that's something to keep in mind. Temperature is a state function, volume's a state function. So you want to focus on things that you measure directly. It's pathway independent. Those are state functions. And what we're going to be talking about is entropy is also a state function. And entropy is disorder. So that's what you want to focus on in this chapter. So one of the calculations you may have is how do we determine the change of energy of a substance or our system. And so the change in energy is equal to Q plus W, which is heat plus work. Heat plus work. So let's read the problem up here. It says calculate the overall change in internal energy in joules for a system that absorbs 188 joules of heat and does 141 joules of work on its surroundings. So what you want to do when you're working with these types of problems is draw a picture, and you're saying that the system absorbs 188 joules of energy, and that the system does 141 joules of work on the surroundings. So that means the work is going out of the system and into the surroundings. So when we look at the equation, we have Q is a positive 188 joules because it's absorbed by the system, but then the system does 141 joules of work on the surroundings. That's why it's a negative value. It means it's going out of the system into the surroundings. So the overall net change for the internal energy of the system, what's ever inside this box here, is 47 joules. All right, so we gain some energy, we lost some energy, but the net is we still have 47 joules of energy left in the box, and that is energy that has the ability to do work. So heat absorbed is an endothermic process, so you define the system, heat absorbed by the system, then heat will be a positive value. If heat is released by the system, it's a negative value. We call that an exothermic process. And if work is done on the system, then work is positive because the work is going into the system. And if work is done by the system on the surroundings, then work is negative. And again, this should seem like a review from 105, but I just find that if you don't get this part, then when we combine entropy and enthalpy later on to calculate delta G, you get lost. So that's why we're spending a little time here. So here's what it looks graphically. Here we have the system. And remember, a piston generally represents atmospheric pressure. This is the way we represent atmospheric pressure in a picture. And so this system is releasing heat to the surroundings. So Q is less than 0. It's going to be a negative value, exothermic. The system is pushing against the atmosphere. And so what you notice is if this is where the atmosphere was, and then a gas is generated in this reaction, and it pushes against the atmosphere this much, this is the change in volume from here to here. And that's where we get work equals negative P delta V. So delta V is a positive value because the system is pushing against the surroundings. The pressure is always going to be positive because you can only have zero pressure or some positive value. So if you have a positive value for the change in volume and a positive value for the change in pressure, positive times a positive is a positive, but then we have a correction factor of a negative here to make work a negative value to say the system is doing work on the surroundings. So remember, negative, the system is doing work on the surroundings. It's giving off heat to the surroundings. And then here's the opposite. The heat goes into the system. Q is greater than 0. Endothermic work is done by the surroundings on the system. We see the atmosphere pushing down on the system, and so work would be positive here. We're adding work into the system. So we saw that delta U, which is the change in internal energy, is equal to heat plus work. We've substituted in for work negative P delta V. We substituted in for work negative P delta V. So now we get Q, the heat at constant volume. This should be a subscript. Q at heat at constant volume is equal to the internal energy, because if the volume stays constant, then delta V is 0, and so we have 0 for the work done. And so we talked about this in 105. This is where we talked about delta H. This is why we're doing this, is to talk about enthalpy. So Q at constant pressure is equal to, there's a typo here, there should be a delta U here, an internal energy, there should be a U there, plus P delta V. And the reason why I didn't the reason why I didn't catch that is that comes up to be delta H. So there it is. Delta H equals delta U plus delta P delta V. So Q at constant P becomes that, and that's what you're doing in a lab. You have a beaker, it's open to the atmosphere, you're assuming the pressure is not changing through the course of your chemical reaction, so any heat being exchanged is due to the internal energy change and pressure volume work. So I'm not going to go through this complete slide. What this is, they're substituting in, and they're trying to, this is the proof to prove that delta H, the change in enthalpy, is equal to heat at constant pressure. That's all that is. You don't need to know this. You're not tested on that. I'm just showing you where delta H comes from, because people need to have an understanding of how we get from delta U equals Q plus W to Q at constant pressure equals delta H. And again, delta H, just like internal energy, it's going to be final minus initial. Our final in chemical reactions is going to be products minus reactants. It's always going to be products minus reactants. All right, so here that was a review. That was a review getting you ready for chapter 16. Now we start chapter 16, and the first topic is spontaneous process. So spontaneous process or processes are things that you know will happen spontaneously, like this pen. You know when I let go of it, it's fallen to the table. That's a spontaneous process. You see water go over a waterfall, you never see it go reverse, like it comes up the stream and jumps up. You never see that. Ball always rolls down the hill, doesn't roll up the hill. Then we get a little more technical, like when you look at ice, ice will spontaneously melt to water if the temperature's right, all right? Or water will spontaneously freeze to a solid if the temperature is right. So now we have a temperature dependency there. So, process that occurs under a specific set of conditions. So we are looking at pressure, we're looking at temperature. If it occurs, we call it a spontaneous process. If it doesn't occur, we call it a non-spontaneous process. Now, here's what I want you to remember about non-spontaneous. A lot of people go, well, I don't need to worry about non-spontaneous. If it's non-spontaneous in the forward direction and the reaction is reversible, it will be spontaneous in the reverse reaction. All right? So don't just discount non-spontaneous. Go, I don't need to know that. It's not that. Yeah, sometimes we're going to be looking at the reverse reaction. That's coming up. So if it's non-spontaneous in the forward direction, if it's a reversible process, it could be spontaneous. It'll be spontaneous in the reverse reaction. So here's some examples. We've talked about ice melting at room temperature, specific conditions. We know we're assuming normal atmospheric pressure. We're assuming room temperature is 25 degrees Celsius. And so ice melts at room temperature. That's a spontaneous process. If I add sodium to water, it's a violent chemical reaction. It makes sodium hydroxide and hydrogen gas. That's why we call sodium an alkali metal, because it makes a strong base. But that's a spontaneous process. We talked about the ball rolling down the hill. Also, rusting is a spontaneous process. So that's why your cars eventually will rust out. I don't know if you've seen those, the show, like after the humans are gone, stuff starts falling apart because everything starts rusting. Yeah, that's going to happen. And then water freezing at negative 10 degrees Celsius. Under those set of conditions, we are below the freezing point, and we assume, again, 1 atmosphere pressure, since they're not talking about anything else, and so that's a spontaneous process. We don't expect ice to melt at negative 10 degrees Celsius at 1 atmosphere pressure. All right, so here's a couple exothermic reactions that are spontaneous at room temperature, and I would hope that you would know that the first one is spontaneous, and that this is how if you're heating your house or apartment with gas, you are generally using methane, which is CH4, reacts with oxygen, that combusts to make carbon dioxide and water. You see the delta standard enthalpy is negative 890.4 kilojoules. That tells you it's an exothermic reaction. And what that is saying is, here is the energy in methane and oxygen. You add a spark, and bam, it drops down to this energy, which is carbon dioxide and water. So just like dropping this pin, it was spontaneous. We would expect methane reacting with oxygen and forming lower energy carbon dioxide gas and H2O liquid. That would be a spontaneous process. So generally, exothermic reactions are spontaneous. Not always though. So we're going to find out there is another player in the game called delta S, which is entropy, the disorder. And so disorder has a part to play as well. But if I had to guess, if I only had that reaction to go by, the two things that would tell me that's spontaneous is I think about the heating of a house, and I know that happens spontaneously, and then that big exothermic value there. That's what would tell me, if I had to guess, it's spontaneous. All right. The second reaction, a little bit harder, but here's what you know. It takes energy to break bonds. It always takes energy to break a bond. When a new bond is formed, generally energy is released. And so that's what we have here, is that when the hydrogen ion reacts with the hydroxide ion, there's an attraction. And when that bond occurs to make water, energy is released. Not much, negative 56.2, nothing like the methane. But generally when bonds are formed, energy is released. And again, exothermic reaction, generally we would assume that that would be spontaneous. Now, let's throw a wrench in it here. Look at the last one. This exothermic reaction is not spontaneous at temperatures above 0 degrees Celsius. So here we're trying to go from liquid water to solid water. So again, we're increasing the, we're going from a liquid phase to a solid phase. It's exothermic. It releases heat. This is why you put liquid water in the ice tray, and then eventually, after it's been in the freezer, it changes to a solid. You have to pull the heat off of the liquid water. And so it is an exothermic reaction. But this reaction is not spontaneous at room temperature. So even though it's exothermic, you might think, oh yeah, that's going to be spontaneous. It's not. It's not spontaneous until we reach the correct temperature. So exothermicity favors spontaneity. It's a good indicator, but it's not the only indicator. So generally, exothermic reactions got a better chance of being spontaneous than endothermic reactions. All right, so here's the other player, entropy. Entropy, if you don't like the word entropy, substitute the word disorder. That's what it is. It's disorder. So the symbol for entropy is a capital S, and it is how spread out things are, how disorder, how many points are available. If you want to think of entropy as like this, if this was a container of gas, all the gas molecules have to stay within this container. If I take the top off, now the gas can occupy any place in this room. Much larger volume than what's in this container, and so that's an increase in entropy. The more positions atoms or molecules can occupy in space, the greater the entropy. Same thing with your clothes, right? You have to take energy to fold your clothes up and put them in the dresser. It's very easy for them to get out of the dresser and be spread all over the place. So the universe moves towards entropy, more disorder. And just as spontaneity is favored, a process being exothermic, spontaneity is also favored for an increase in the system's entropy. Now, here's the key to that sentence there, system's entropy. What you're focused on studying, the system's entropy. The greater disorder in the system, the more likely it is to be spontaneous. So you know this. You know that up here we have a diagram where all the gas molecules are on one side of the container. We have a barrier there. When we remove the barrier, those gas molecules are going to spontaneously occupy that additional space. Same thing as this container that we've talked about. All right, so how do we calculate entropy? So here's what's important on this slide in that you've got to be very specific. Are you talking about the entropy of the system or the surroundings or the universe? So the little subscript is important. System, surrounding, or universe. Now, generally, what we focus on is the entropy of the system. Because if I say this is my system, I have a defined barrier. I know exactly what in space what this is, so I can look at the disorder within this. Once the gas escapes here and goes out into the room, then it gets to be a little bit harder to talk about entropy. Because now you're talking about a volume the size of the room and where are the gas molecules or where are the atoms in that space. You can tell that gets a lot more complicated. All right, so that little circle, the standard symbol, means something. Okay, so standard entropy is the absolute entropy of a substance at 1 atmosphere of pressure. So when we have that little standard on the S, we're assuming 1 atmosphere of pressure. Make sure you understand that. That little, it doesn't look like much, but that little degree symbol represents all conditions at 1 atmosphere of pressure. Now, that doesn't talk about temperature. It just says the standard entropy. So here's some values of standard entropy. And what I want you to get out of this slide is that you can definitely see that gases have more entropy than liquids. So H2O liquids, 69.9. And then notice the units. It's not kilojoules per mole. It's joules per Kelvin mole. So when we start trying to add a delta H and a delta S together, we're going to have to convert either the delta H, which is generally in kilojoules per mole, to joules per mole. And we're going to have to multiply that entropy by a temperature to get rid of the Kelvin in the denominator. So you're going to see generally entropies multiplied by temperatures in Kelvin before you add or subtract that from the enthalpy. So watch your units carefully. So water liquid 69.9, water gas 188.7. Huge difference. Gases have the most entropy. Sodium solid 51.05, liquid 57.56, not much of a change. Why is there not much of a change? Because we've talked about that solids and liquids are the condensed matters. That in solids and liquids we have intermolecular forces that hold these atoms or molecules together. We haven't overcome all the intermolecular force like we do in a vapor, and so that's why their entropies are pretty close to the same. Now, when it becomes sodium gas, that means you have to add energy to get the liquid to become a gas, and then the entropy as a gas jumps up tremendously, 153.7. All right? So then you look at helium and neon, both noble gases. Why is neon's entropy greater than helium's? Anybody have a guess? So here's what you're going to do to make, because this is a good question too. This is a good one. So you're thinking about, on the periodic table, helium's in the first period, neon's in the second period. What's the intermolecular forces that would hold, if these were liquids, what would be the intermolecular force that would hold these together? It'd be dispersion, that's right, dispersion forces. That's the only force that's holding the liquid together. Now, these are gases, so the intermolecular force is pretty much non-existent. So now we've wiped out the intermolecular force as a choice. So then what do you have to go with? What? Electronegativity, that's a possibility, but they, for two molecules, just looking at helium and neon, they're not interacting with another molecule. We assume gases are independent, so we're not looking at, and they're neutral charge, so that's not it. Got another guess? There you go. There it is. It's all about mass. That's what it's about. And that's the only thing it's about. When you've knocked out the intermolecular forces and electronegativities, electrostatic forces, and again, generally if we're talking about ideal gases, we assume these things aren't attracted to one another. So molar mass is the correct answer. Good job. That's what it's all about, thinking about it. All right? Then here's the one I think it's really important too, is look on that next column, the carbon, diamond, carbon graphite. Now here's the word you need to know. What is, when you have two different structures of the same element, what's it called? Two different structures of the same element. Anybody got a name for that? Allotrope is correct. Good job. Allotrope. We talked about that in 105 as well. Allotrope. So allotropes are like oxygen and ozone, carbon, diamond, carbon, graphite. And what you know is we've seen diamond. Diamond is a tetrahedral structure. It's a network covalent compound that we talked about in chapter 10. It was in the back of that chapter. So network covalent. Graphite, it was hexagonal planes of carbon, and we talked about last time that that's what happens when you write out with your pencil, that the graphite shears off, lands on the paper, and that's how you see the writing. So because carbon graphite has that ability to move off, it has a slightly higher entropy. Okay? So that's a cool one. Allotrope's important because that's a good way to distinguish between those two, is that carbon graphite, because it's got a little bit more movement, it's not as rigid, not as hard as diamond, probably going to have a little bit more entropy. Same thing there, oxygen and ozone, those are allotropes. Now, the structures may not be that much different, but they are. They actually have some. Think about diatomic oxygen versus 3 oxygens bonded together, and then think about the movement of those atoms. Ozone's going to have more movement, more possibilities of different types of movements, and it has more mass. So again, higher entropy. All right, so for a given substance, always remember that the liquid phase has more entropy than the gas phase. We've already seen that. These are just some points that we've already made here. Bottom one is the one that I think most students have the hardest time with. That's why I brought it up. The larger the molar mass, the greater the standard entropy. So if all things are the same, no electrostatic forces, no different intermolecular forces, molar mass comes into play. All right, so for two substances in the same phase with similar molar masses, the substance with the more complex molecular structure has a greater standard entropy. You need to write that one down. So this is, you got two substances that have the same molar mass, and we talked about this when we talked about intermolecular forces. We said that like pentane, flat pentane, had stronger intermolecular forces, stronger dispersion forces than something like T-butyl, which was 3 carbons and then it was a branched-looking substance, made it more spherical-like. So you may want to go back and look at that in a previous slide. But the more complex the structure, if the masses are approximately the same, the more entropy. Now, this is what I'm talking about, the difference between oxygen and ozone. Now, they actually give examples of fluorine and oxygen, or ozone, and then kind of show you what's going on here. So, I'm trying to think why they did it that way. 38 and 16, it's not quite that. But, so look at the fluorine, the first one. Diatomic fluorine. The only movements that diatomic fluorine can make is the fluorines can expand backwards and forwards, all right? So that's about the only position it has. It's either doing this or this. You say, well, could it go like that? Well, that's going to cause that to go like that, right? So that's pretty much the only movement it has in one plane. Now, the other thing fluorine can do, if you look down in part B, it can spin on the axis. Can spin this way or this way, but that's pretty much it for fluorine. So, just looking at this picture, you can see that fluorine cannot occupy as many positions in space than ozone. So, if you look at ozone, yes, it can do, if you look at the first line of ozone, it's pretty much what fluorine's doing. It's just oscillating back and forth like this. Then you can get an asymmetric stretch, which is what you see in line 2, where one moves up and the other one moves down. And then you can get some wagging up and down like this. And you go, why do I need to know this? Well, if you're taking organic chemistry, this is how you're going to determine, using maybe infrared, that what the substance you have. You'll start looking at these stretches and wags or scissorings, and that's going to give you an indication of what substance you have through an IR. So these movements become really important, but the reason why we're talking about them here is you can see with ozone, because it has a lot more positions available for each oxygen atom to occupy in three-dimensional space, it has more entropy than oxygen. And then if we look at ozone in that last line, you can see its rotations look more complex. It's still the same rotations, but look how many places it occupies in space versus the diatomic fluorine. So that occupying space is important. Occupying space. More positions that can be occupied, the higher the entropy. All right, we've already talked about this in cases where elements exist in 2 or more allotropic forms, carbon, diamond, carbon, graphite. The one that's more mobile has the greater entropy. Diamond's not as mobile, it's hard, doesn't really flex that much. Graphite peels off when you write on the paper, has a greater entropy. All right, so how do you calculate standard entropies? we're going to use a balanced chemical equation. This is the general form. Lowercase a represents coefficients. Capital letters represent the substances. So we have A plus B forms C and D. Delta S, just like delta H. So we're looking at standard entropy changes for the reaction. It's always final minus initial. It is products minus the reactants. So you have the lowercase c, which is the coefficient in front of the substance C, multiplied by the standard entropy for C, which you will find in a table. You have to look in a table. I noticed your homework problems, you click on a little blue hypertext and a table pops up for you. And so you're going to add the amounts for standard entropies for the products, the summation of that minus the summation of the coefficients times the standard entropies of the reactants. Now, the most common mistake here that I see on people's homework is when they subtract off the reactants, make sure you calculate everything in the brackets first before you subtract it. So what I see students do is they do the first one, C times the entropy, standard entropy for C, plus D times the standard entropy of D, and then they go minus A times the standard entropy of A, and then they say plus B times the standard entropy of B, and that gives you the wrong answer. You want to add up everything in the brackets first and then subtract the left bracket minus the right bracket. If you'll do that, that one extra step, just make sure you get them done in the brackets first, you'll probably get the answer right versus the other way. So just write it down and don't make that mistake, because it's the worst mistake. You understand the concept, but you don't get the right answer on the quiz or test or assignment just because you're rushing through it a little bit too fast and not methodically going through it. All right, so I'm going to show you some examples, and I'm not going to do all of these. I just want to show you the process of how you would do a problem like this for your homework. So the first one, we have calcium carbonate, which is a solid, going to calcium oxide solid, which is called quicklime. This is actually done in Lexington, Kentucky, this first reaction. You go to the rock quarry, you dig out limestone from under Lexington, you heat it up, and it becomes quicklime, and carbon dioxide is given off. So if you look at that first reaction, do you think the entropy is going to increase or decrease? And why do you think it's going to increase? That's right, because it's giving off a gas. So you started with the solid, and yes, you get a solid as a product, but you also get a gas as a product, and that's going to be an increase in entropy. So starting off on this problem, you want to look at the problem like that and go, yeah, I expect this to have a delta S that's going to be positive, because increase in entropy should be a positive value. So if you don't get a positive value when you calculate this out, that's your flag to say, maybe I've done something wrong. All right? So in order to do this problem, you have to have a table. You have to have a table of standard entropies. And again, that's a hypertext in your homework, or it's looking in the back of the book to find those standard entropies. And remember, standard entropies, the units are joules per Kelvin mole. So it's going to be products minus reactants. And so here we go, 39.8 joules per Kelvin mole for calcium oxide, a product, plus 213.6 joules per Kelvin mole for the carbon dioxide. And here's something to think about when you're doing the problem too. You expect the gas to have a much higher entropy than a solid, and it does, 213 versus 39.8. And then you're going to subtract from that, since there's only one reactant, it's easy, you don't have a bracket there, so you can just say minus 92.9. It's all 1 to 1 to 1 mole, so you don't have any multiplier there. So your answer comes out to be 160.5 joules per Kelvin mole. That's a positive value, and that's what you would expect, that you would see a huge increase in entropy because you generated a gas. All right, questions on that one? Easy. Just be methodical about it, because these are easy questions. These are ones you should definitely get, all right? It's just a matter of being methodical about writing it all down, watching your units, and so forth. The next one, the difference between the first one and the second one is the second one for nitrogen plus hydrogen forms ammonia. This one may be a little bit harder to guess if it's going to be a positive or negative entropy, but if I had to guess, maybe negative would be it, because on the reactant side you have 4 moles of gas. On the product side you only have 2 moles of gas. Now, mass comes into play here as well, and ammonia is heavier than nitrogen or hydrogen. So that one's not just easily be able to look at it and say for sure that it's going to be a negative entropy change. But going from 4 moles to 2 moles, almost, and if you had to guess, a negative entropy change would be it. Now, here's the difference. Here we have a multiplier. You have the coefficients of 1 in front of the nitrogen, a 3 in front of the hydrogen, and a 2 in front of the ammonia. Don't forget to multiply the entropies by those coefficients. So 2 times the entropy of ammonia minus, here's where the bracket becomes really important. Put a bracket and say 1 times the entropy of nitrogen at 191 there, plus 3 times the entropy of hydrogen at 131. Close the bracket. Make sure you add up everything in the bracket, and then subtract that from the 2 times 193. If you do that, you won't make any mistakes. You get the right answer, and you're happy for it. Now we'll skip the last one. It's not really worth it. Same thing, though. Same process. All right, so you need to know which processes lead to an increase in entropy. Melting makes sense. You're in a rigid, defined solid. Solids have definite shape, definite structure, strong intermolecular forces. You heat them up, you apply energy, they start to loosen their intermolecular forces. They allow each molecule or atom to slide over one another. They can occupy more positions in space, so melting is a higher entropy. Vaporization or sublimation, when we go from a solid phase or a liquid phase to a gas phase, we're going to see huge increases in entropy. Temperature, remember the definition of temperature really is how fast something's moving. Now it could be just a vibration like the table. Yeah, it's not moving, but if we look at the molecules in the table, they're vibrating. So the faster things vibrate or move, the higher the temperature. So temperature increases, increase in entropy. And reactions resulting in a greater number of gas molecules. We've already seen that twice there. So reactions that have greater numbers of gas molecules. So this is what temperature looks like. This is a Boltzmann distribution. So you need to be able to interpret a plot like this. The yellow, notice all the molecular speeds are kind of bunched together, and the peak is at a lower value on molecular speed than the possibilities of the higher temperature. So the tail goes out further on the higher temperature. So if you just take a point here, like you cut right through here, you can see there's more area under the curve of the red, higher molecular speeds, higher entropies than under the yellow. So the possibility, there's a larger possibility of higher entropy, larger molecular speeds and greater entropies. All right, so I put this slide up here because this is one of these challenge slides. And if anybody gets this slide right in here, I'm going to be blown away, all right? So if somebody can tell me what's going on this slide, you understand this backwards and forwards, and you're in great shape, all right? So the first one, I would expect everyone here to say, this is an increase in entropy. And you go, why is it? Well, you got ammonium nitrate, fertilizer, you put it, and it's a solid, you put it in water, and the 2 ions separate. Water gets in between them, forms a cage around them so they can't get back together. So we say that's soluble, it's dissolved into the water. And the entropy is 108.1. It's a positive change, and it should be, because now these ions can occupy more positions in space than the solid could. All right, so now we're going to look at the second reaction. Aluminum chloride, it's a solid, and it dissolves into an aluminum ion and 3 chloride ions, and you would expect probably that, yes, there should be an increase in entropy. An increase in entropy. But look at it. Its entropy is a negative 253.2. We actually see a decrease in entropy. Does anybody know why it's a negative 253.2? Oh, you're right. You're getting there. What happens to that? What is it with the charge on the aluminum? Okay, so let's kind of, because you're on the right track, you're getting there. So here's what it is. You got aluminum with a 3 positive charge, and forget about the chloride because we separated those two. So what is aluminum 3 positive going to interact with in a solution? If not the chloride, what would it interact with? What? Water is correct. Remember, water is a polar substance. It has a partially positive charge on the hydrogens and a partially negative charge on the oxygen. So the oxygen see this huge positive 3 charge, and all the water molecules start orienting themselves so that the oxygen is close to the positive 3 charge on the aluminum. And so where the water was just, moving around wherever it wants to, now the aluminum's in there and it's locking on to the aluminum ion. So that's electrostatic attraction. That is a part. That does play a part. So the electrostatic attraction between that aluminum 3 positive and the partial negative charges on the oxygens of the waters cause the waters to lock in to that aluminum 3 positive, and that's why we see a decrease in entropy. Same thing for the last one there too. Iron 3 positive. And the reason why I bring this up, because you say, do I ever need to know this? It does start to change the acidity of the solution. And you may come across that at some point, that these ions, aluminum chloride and iron 3 chloride, both can change the acidity of the solution because of that interaction. So good job. That's what you got to do as a scientist. You got to think about it. There is a solution. There is a way to get to that ending, and then you got to start drawing all the information that you know that you've gotten in 105 and 107. Started putting it all together to come up with an explanation. That's what you're trying to do here. All right, let's get our our clickers out. Whatever we're going to use here. You've got 5 questions you're going to answer here. All right, we've been talking about entropy. Entropy is disorder. We got 5 questions describing. We have a process here. For the first one, we have the decomposition of calcium carbonate solid to give off calcium oxide solid and carbon dioxide gas. And what I want to know is the change in entropy. Is that going to be a positive value or a negative value? Remember, positive means an increase in entropy, So I'm going to give you 30 seconds on these because it's pretty much you either recognize it or you don't. So we'll go 30 seconds on question 1 there. So you choose either A or B, positive or negative. All right, let's see where everybody is in class. All right, 92%, better than 87% last week, or on Tuesday. All right, although there is some people, 8%. Remember, negative means a decrease in disorder, decrease. And because we talked about this one, we said that you're going from a solid to a gas being formed. That's why this is a positive increase in entropy. All right. Next one, question 2, heating bromine vapor from 45 degrees Celsius to 80 degrees Celsius. We're at 98%. I think we're going to get to 100. I think we're going to get to 100. All right, so it is an increase. Temperature increase means increase in entropy. All right, condensation of water vapor on a cold surface. All right, condensation of a water vapor onto a cold surface. Still at 98%. All right. Come on, you guys. 2%. Let's make it 100. All right. So, again, you're going from a gas to a liquid. That's what condensation is. Gas to a liquid. Gas has lots of disorder, lots of places it can occupy. Water as a liquid is condensed phase. It's sticking to that surface. Doesn't have as much places to occupy as a liquid. Therefore, negative entropy change. All right. Next one. Maybe you've seen this reaction. So if you're in the lab, ask somebody to open up a bottle of ammonia. Liquid, it's generally liquid, it's not a gas, but some of that gas will come out of the bottle. If you have a bottle of hydrochloric acid over here in this hand, up here there will be a cloud formed between the two bottles, and that is ammonium chloride solid being formed out of the vapor, out of the gases of ammonia and hydrogen chloride. So, you have two gases, they react with one another, and they form ammonium chloride. Positive entropy change or negative entropy change? Oh, we have a decrease, actually. Oh, come on. So a solid occupies less space than a position, solid occupies less positions in space than gases. That's a negative entropy change. A decrease, let's do it this way. If that's what's giving you as a positive, a decrease in disorder is a negative value, a decrease in disorder. All right, last one. So think about it. You got a glass of water. You take a scoop of sugar, solid. You drop it into the glass. You stir it up, and the sugar dissolves into the water. So now you have a solution, a sugar solution. All right? So think about it. Is the sugar occupying more space in the water than it was as a solid? That's what you need to think about. Oh, that was even worse. So sugar, it does occupy more spaces in the water than as a solid. It's more mixed. It's got more positions it can occupy in that water than just sitting there as a teaspoon of sugar. All right. So make sure you know those. Those are important. I guarantee you see something like that on an exam. We've got to figure out whether you can see what a positive entropy increases versus a negative entropy. All right, so I'm not going to go through the answers. You can look, I put those in there because some of you guys go back and review these slides, and so I want you to see what the answers are when you go back and review it. All right, next part is the change in entropy of the surroundings. So why this is important is when I let's say I have a fire here. I'm going camping. I've got a campfire here. I am burning the wood. The wood is increasing the heat of the surroundings. And so the wood burning is an exothermic reaction. So that's delta H is negative. It's an exothermic value. So as the wood burns, it does increase the entropy of the surroundings because the surroundings get warmer. So we want to look at the relationship between enthalpy and entropy, and this is the beginning of it. And we're going to talk about the second law of thermodynamics and the third law. All right, so here is what you need to know is that the change in entropy of the surroundings is proportional, that's what that fancy symbol is proportional to the negative enthalpy of the system. So you say, what does that mean? Okay. If you're burning this fire, it's giving off heat, it's got a negative value, so it's a negative, let's say it's a negative 100 kilojoules per mole for burning this campfire. Negative 100 kilojoules per mole, I plug it into this equation, so a negative times a negative gives me a positive entropy change for the surroundings. That makes sense. I'm burning this fire, it is increasing the temperature of the surroundings, and that increase in temperature causes a positive entropy change of the surroundings. So, the change in the entropy of the surroundings is inversely proportional to temperature. All right? Inversely proportional to temperature. That's a 1 over temperature. So if we add those two things together, we get the change in entropy of the surroundings is equal to negative the delta enthalpy, or the enthalpy change of the system divided by the temperature. And that's the equation you're going to use to calculate some problems on your homework. So in your book, they don't use the word delta H. They call that Q reverse. So when you're looking in your book at this particular equation, they use a Q here instead of a delta H. And it's the same thing, because what is Q? Remember what delta H is. It's enthalpy, it's heat under constant pressure. We're assuming the pressure is not changing through the course of the reaction. So they can be used interchangeably. All right, here's the second law of thermodynamics. The change in entropy of the universe is increasing. It's always going to have a positive value. All right? The change in the entropy of the universe must always have a positive value. And you go, how do they know that? Well, so we are operating under the theory of the Big Bang, right? So everything started from a point, and then it expanded out into the void. And so now all the particles of matter can occupy a larger space than when it was in a point, or a smaller volume. And so if we assume that the universe keeps expanding, we assume then that the change in entropy of the universe is always positive. So that is the second law of thermodynamics, that the change in the universe is always positive. Now, the second sentence. An equilibrium process is one that does not occur spontaneously in either the net forward or net reverse direction, but can be made to occur by the addition or removal of energy from the system. Now, I haven't heard this theory as much in the last 10 years, but there was a debate at one time. Does the universe, are we in the forward reaction of the universe, and that's why it's constantly expanding? And that at some point, we're going to go towards equilibrium, where once we get out so far, just like with vapor pressure, once you get so much vapor, then some of the vapor starts to condense back into the liquid. So then does the universe start to contract? And they call that the big crunch. And so things would start contracting. I haven't heard that theory as much lately, but that if you believe that we're not in the equilibrium, that the universe will reach an equilibrium, then you would say we're in the forward part of that equilibrium and not the reverse part yet. But that doesn't seem in favor right now. All right. Determine if each of the following is a spontaneous process, a non-spontaneous process, or an equilibrium process at a specified temperature. Okay, this one gets a little more difficult. So they want you to be able to calculate these, to figure out what these are, and let's just kind of show you what this looks like. So, first reaction, hydrogen plus iodine gas forms 2 moles of hydrogen iodide gas. And so how do we calculate whether this reaction is spontaneous or non-spontaneous? Well, you calculate the standard enthalpy of the reaction, entropy of the reaction, all right? So you go to your table and you calculate what the change in entropy is. It's products minus the reactants. That's why you see 2 times 206.3 minus the 2 reactants, hydrogen and sulfur, and you calculate that and you get 21.03 joules per Kelvin mole. Now, you also need to, if you want to determine whether the reaction is spontaneous, there's 2 players now. There's the delta S and there's the delta H, entropy and enthalpy. So you need to calculate the enthalpy of the reaction, and this is what you learned in Chem 105, and this is why I did this part at the beginning of the class. You need to calculate the delta H of the reaction, and it's final minus initial again. You look in a different column of the table where you have the standard enthalpies of formation. That's what the standard delta H with the little subscript F, standard enthalpy of formations. Products minus the reactants, and you get negative 10.5 kilojoules per mole. All right, so now I want to calculate the standard entropy of the change of the surroundings. You go, why do we have to do that? Well, let's go back. Here's what we need to know, that the standard entropy change of the surroundings is equal to negative delta H of the system minus divided by the temperature. All right, so we calculate the standard entropy of the surroundings, negative delta H divided by T, and we get 0.0385 kilojoules per Kelvin mole. And you go, well, that's not going to, I can't add that to delta S of the universe that we, or delta S of the reaction that we did, because up here with the delta S of the reaction, the units are joules per Kelvin mole. So we have to convert from kilojoules per Kelvin mole to joules per Kelvin mole. So now we have the change in entropy of the surroundings. We have the change in entropy of the reaction, which is the system. And so the change in entropy of the universe is equal to the change in entropy of the system plus the surroundings. So we add these together, this number and this number that we just calculated there, and we find out that the change in entropy of the universe is 59.5 joules per Kelvin mole. Because it's a positive value, you know that this reaction is spontaneous. All right, so let's talk about this one more time again. You look at the reaction. That one's a hard one to tell whether that's going to be spontaneous or not. It's not. You'd say, well, it's 2 moles of gas on both sides. It's at 0 degrees Celsius. It's probably got a temperature dependency to it. And you go, I don't know for sure if that's going to be a positive entropy change or a negative entropy change. So I do know there's standard entropies table, and I can calculate the standard entropy of the reaction, which we've been doing. I know how to calculate the standard enthalpy, delta H of the reaction, because that's what we learned in Chem 105. And then I can calculate the standard entropy of the surroundings by knowing that delta H of the reaction over the temperature will give me the entropy change of the surroundings. And then the key is that the standard entropy change of the universe is the system plus the surroundings, and now you have those two values and you can add them together, and once you add those two together, you now know that it's a positive change in the universe and it is spontaneous. I'm not going to do the other ones. I just thought this would give you an example of how you're going to use those equations. Oh, here's one, though. I do want to talk about the last one. When you plug in the value for delta S of the reaction and delta S of the surroundings, you actually come up with the value 0 or pretty close to 0. If you come up with a delta S of the universe equal to 0, we assume you've reached equilibrium. that the forward and reverse rates become constant, and we're at an equilibrium point. So that's where you're like in between, maybe like, solid sodium and a liquid sodium. All right, third law of thermodynamics, last one. It's the easiest one. Entropy, unlike enthalpy, has a specific reference point as to what is zero entropy. So with delta H, we had to define artificially that the standard enthalpy of formation of a element in its standard state at 25 degrees Celsius, 1 atmosphere pressure, has a standard enthalpy of 0. That was our defining point. Entropy actually has a defining point. You can actually calculate just S, not delta S. You can actually calculate the S. And that is a perfect crystalline solid at 0 Kelvin. That means no movement of the electrons inside the crystal has an entropy of 0. That's the third law of thermodynamics. A perfect crystalline solid at 0 Kelvin, absolute 0, has an entropy of 0. So we can actually say S equals 0, not delta S. S equals 0, and that's our reference point for all other entropies. That's why you saw on the entropy tables, everything's positive. Everything's positive. Whether it's a liquid, solid, gas, all of those have a positive entropy. And this is what it looks like. So here we go back to this is a different type of heating curve, but it's the same thing. You're going from a solid, and you have a lot more less entropy here. Then it breaks to a liquid, so we're going through the delta S of fusion instead of the delta SH of vaporization. You have delta S of fusion. Then you heat this liquid up, and then you go through a delta S of vaporization just like you go through the delta H. Now, you don't have to know that. That's not part of the exam, but that works the same way. So the first thing I want to do is I want to talk about delta S again. That was one of the last things that we covered. And just want to make sure that we understand what's going on before we start introducing a new term today, Gibbs free energy. So this is what we're going to focus on today, Gibbs free energy. Remember, energy is the ability to do work, and we calculate Gibbs free energy in order to help us determine whether the reaction is going to be spontaneous in the forward direction or not. So Gibbs free energy is going to be the term that allows us to determine whether a reaction is spontaneous or not. Now, just because a reaction is spontaneous does not mean it happens immediately. So hopefully you've read about diamond. Diamond, if you look at just the thermodynamics of diamond should spontaneously convert back to the carbon like you're writing with your pencils. But we don't see that happen, and that's based on another theory, or laws of kinetics. So we'll talk about kinetics later on this semester, but right now we're focused on thermodynamics. We're trying to determine whether a reaction is going to be spontaneous. So we use Gibbs free energy to determine spontaneity. And then we have an equation there, delta G, which is the change in Gibbs free energy, equals delta H, enthalpy. That's why I spent so much time last week to talk about enthalpy. So if you don't remember enthalpy, or you missed last week's lecture, you may want to go back and read about enthalpy. Exothermic, endothermic. Exothermic reactions tend to be spontaneous, but that's not the only driving force. And we learned last Thursday that the other driving force of why a reaction occurs is entropy. So Gibbs free energy equals the enthalpy change minus T times the entropy change. And then the last one, the little knot symbol there, that makes it standard Gibbs free energy. And the reason why we work with standard Gibbs free energy, these values have been calculated for us, and we can find them in a table, and we can use them in the table to calculate Gibbs free energy of reactions. So that's what we're going to focus on today's lecture. All right, so this is from last lecture. I just want to keep stressing what's going on here. So last lecture, the main focus was entropy. We looked at things like ice melting, that is a positive entropy change because we're going to more disorder. And that's what I said. If you don't like the word entropy, swap out the word entropy for disorder. All right? So entropy, the higher the entropy, the more disorder. So there is a relationship between entropy and enthalpy, delta H. And that's what this slide, this is what we talked about the last time, that if you set up a fire outside near, a campfire, you have the wood is burning, that's an exothermic reaction. And that exothermic reaction heats up the surroundings. And we know that entropy is directly related to temperature. The higher the temperature, the more movement of the atoms or molecules, and the more entropy. So that's what this is showing, that first line, is that the change in entropy of the surroundings is proportional to negative the delta H of the system. The system is your wood burning. That's what you define as your system. And the heat coming off of that system affects the entropy of the surroundings. So we know it's an exothermic reaction. If you plug in a negative value for delta H here, because it's exothermic, negative times a negative makes a positive, and we get a positive change in the entropy of the surroundings. The entropy change in the surroundings is also inversely proportional to temperature. All right? So when we combine those two lines together, we get that the change in entropy of the surroundings is equal to negative the delta H of the system, the enthalpy change of the system, divided by T. Now, assume we're going in a forward direction here. That's what we're assuming. So we talked about that last week, and then we put that together, and we find that the change in entropy of the universe is equal to the change in entropy of the surroundings, or the system and the surroundings, all right? So change in entropy of the system plus the change in entropy of the surroundings. When we add those two things together, we get the change in entropy of the universe. And what we said last week was this is the second law of thermodynamics, which says that the entropy of the universe is increasing. So the change in entropy of the universe is a positive value. And that's what that first line said, first paragraph or line, if you want to say that. The change in entropy of the universe must be positive. An equilibrium process, this is going to become really important as we go through Chem 107. We're going to spend weeks on equilibrium in this class, whether it's acid-base equilibrium or precipitation equilibrium. So equilibrium is one that does not occur spontaneously in either the forward or net reverse direction. So just keep that in mind. Probably not so important at this point, but will become important later on. All right, so what I just spoke is how you would write this mathematically. And remember when we started this class, I said, this is the class where you see phenomena, and then you have to explain it mathematically. To me, that's one of those underlying most important points of Chem 107 is we see something happen, and then how do you explain it mathematically? So mathematically, there it is. The change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings, and that must be greater than zero. It has to be positive. All right, so then we substitute in for the change in entropy of the surroundings what we saw on the previous slide, which is negative delta H of the system divided by T. And you go, why are we doing this? Because you've got to learn where it comes from, where the origin is, and how you get from one space to the other. So what we're doing here, we know about enthalpy, we know about entropy. The tricky thing about entropy is you got to measure the entropy change in the system. That's not too bad. We can measure entropy changes in the system. But tell me how much the entropy changes out in the surroundings when I'm burning some wood here. How does it affect the entropy in the back of the room? That gets a little bit more difficult to predict. So we substitute in for the change in entropy of the surroundings, negative the change in enthalpy of the system, which we can measure that very easily. I mean, we define the system and its boundaries, And then we look to see, does the heat leave the system, or does the heat go into the system? So that's a big step right there when we substitute in for the change in entropy of the surroundings, negative delta H of the system divided by T. So as chemists, we generally don't like these, complex things like this where we have a numerator and denominator. So what do? We multiply the entire thing by T. We don't want anything in the denominator. Multiply the entire equation by T. And now we have T, the temperature, times the change in entropy of the universe is equal to T times the change in entropy of the system minus delta H of the system. And that must be greater than 0. All right? Now, mathematically, watch what happens here. Here's something you may have forgotten mathematically. If I change the equality sign, I have to change the values in front, or the signs in front of each one of these terms here. So notice when this sign changes, to make it less than 0, this now becomes negative T delta S of the universe equals delta H of the system. It was negative, now it's positive. And then we get minus T delta S of the system. You go, why are we doing all this? Well, look at this part right here. Negative T delta change of the universe, or delta entropy change of the universe. Well, that's going to help us determine or bring up a new term, which is Gibbs free energy. So here we have it, same thing that we had on the last line. G is Gibbs free energy equals the enthalpy minus temperature times the entropy. All right, that's what this is. Gibbs free energy equals enthalpy minus T times the entropy. Now, you're going, well, what's the difference between here and here? Well, this has definitely changed, you know that. But this is what you got to think about. I can't measure how much enthalpy is in this piece of paper. Just looking at it, I can't say the enthalpy of this piece of paper is 5 kilojoules per mole. Doesn't happen because we're in the universe. Now, what I can do, I can burn this piece of paper, and the heat given off by the paper can be measured, so I can measure the change in enthalpy. So this statement here, where Gibbs free energy equals H minus Ts, or the temperature times the entropy, that's theoretical. That's the foundation. That's the theoretical point. All I can measure is changes. Same thing here. I can only measure changes in Gibbs free energy. I can't tell you how much work this can do, how much energy is in here. I have to burn it. It has to do something in order for me to, there's got to be a change in this paper for me to figure out how much energy is in it. And remember what energy is. It's the ability to do work. So what somebody wants to know is, if I burn this piece of paper, how much work can I get out of burning this piece of paper? How much water can I heat up? How much steam can I make to maybe run a turbine to generate electricity? That's the kind of stuff you're getting into. You're thinking about like a coal-fired generator plant. So remember that G and H, they're both, we can only measure changes. We don't know the exact values of G or H. Now with H, enthalpy, remember what we did. If you go back, we talked about this. We had to have our own 0 point. Our own, when is delta H equal to 0? And what we used was, we set any element in its standard state at 25 degrees Celsius, 1 atmosphere pressure, and 1 mole of it has a standard enthalpy of formation, which is the delta H with the not symbol and a little subscript F, equal to 0. So when you look at carbon on the periodic table, carbon at room temperature is a solid. It's in the graphite form. Its standard enthalpy of formation is 0. So we have a reference point, just like we have a reference point for sea level. Where we say sea level is where water level's out, and that's 0 as far as height goes. And that isn't, we know we could have made it maybe at the bottom of a trench in the ocean at 0, but no, that's our standard for where sea level is. Same thing, we have a standard for what delta H is. Same thing with delta G. Standard Gibbs free energy of formation. Any element in its standard state, standard Gibbs free energy formation will be 0 as well. We have to have a reference point to work from. Now, delta S, we talked about last week. We do have a reference point for delta S. Well, S. We can measure just S, the entropy. And that's the third law of thermodynamics, which says that the entropy, S, of a perfect crystalline solid at 0 Kelvin has an entropy of 0. So we have a defining point for entropy. So we're going to be using this equation to calculate whether a reaction is spontaneous or not. If it's spontaneous, I'm going to get work out of it. You say, give me an example of a spontaneous reaction. I bet if you drove today, you have used a spontaneous reaction in that you stuck your key in the ignition, you turned over the ignition, the electrons spontaneously left the battery. There was an oxidation reaction there where the electrons left one post of the battery. You made the electrons do work. They cranked on the starter, which then causes the pistons to start moving, and you fire up the engine, and then the engine takes over because now you got combustion going on. And then the electrons go from the engine back into the other post of the battery. And so that was a spontaneous process. You made the connection. Electrons spontaneously went through the circuit to crank up the starter. Now, if you stuck your key in the ignition and turned it today and nothing happened, then that means your battery's at equilibrium. It doesn't have that spontaneity, so there's not enough driving force to put the electrons through and crank the starter. So that's what we're going with. That's what we're getting into when we look at this equation is, can I get work out of the chemical reaction? And the three things I'm going to be looking at: enthalpy, is it going to be exothermic or endothermic? The temperature at which the reaction happens, and the change in entropy. Through the course of the reaction, does the entropy increase or decrease? All right? So this slide you definitely need to know. This is what's going to tell you whether you have a spontaneous reaction or not. When you calculate delta G, if delta G is less than 0, you will have a spontaneous reaction. If delta G is less than 0, you will have a spontaneous reaction. If the delta G is greater than 0, it means a positive value, then you have a non-spontaneous reaction in the forward direction, but you have a spontaneous reaction in the reverse direction. But generally we're focused on the forward reaction. So delta G greater than 0, non-spontaneous in the forward direction, that means it's not going to happen. All right? If delta G happens to equal 0, you're at equilibrium. That happens every once in a while. Just like I said, if your battery's dead, it's not really completely dead. It's at equilibrium. I mean, that's the whole thing. Once you fire up the engine starts turning the alternator, or some people call it a generator, and it generates electricity. It reverses the charge so that you're charging up your battery for the next time you need to start it. So when the alternator goes out, then you're just running on the battery. Once the battery goes out, then you're in trouble, right? So that's what we're looking at. We're looking at, does that battery have the ability to do work? It does if delta G is less than 0. All right. Yeah, this is a little bit small. I was wondering how it's going to play here. All right, so let's talk about, I don't think there's anything I can do about it at this point. It looks large on my screen down here. Oh, you got it on your computer, some of you. Let's see if I can, let's see here if I can get out of that and stretch it or something. It's a little better, all right. So this is the really important slide. that you're going to use to determine whether your reactions are spontaneous or not. So if you got it on the computer, great. If you can't see it, you can either move or you can start writing some notes down, but this is an important slide because this is how you're going to determine, based on delta H values and delta S values and temperature, is the reaction going to have a negative delta G. And if Gibbs free energy is negative, then you have a spontaneous reaction. So I'll talk you through it. So here it is. Let's do this too. Let's put up the equation that you're going to have memorized, which is delta G equals delta H minus T delta S. Yeah, let's see. I can try and find one. Let's see if there's one down here. There's a blue one here. Let's try that. And I'll turn the light on here. Delta G equals delta H minus T delta S. And then let me see if I can turn the light on here so it will. Is it this one? No. That's that one. You guys know where the light switch for this one is up here? Well, is it on the panel? I don't think that's it, but we'll try it. Oh well. Okay, so let's talk about this so we at least got, hopefully you can see that one. So the first one, delta H is negative. So if delta H is negative, up on the slide here, is that exothermic or endothermic? Exothermic, so you need to know that. Delta H negative, exothermic, means heat's given off by that substance. Delta S is positive. Does that mean an increase in disorder or a decrease in disorder? Increase. So we have something that's exothermic. We're looking at a system. It's exothermic, it means it's giving off heat. And the disorder is increasing. The entropy is increasing. So you plug it into this equation. So this is a negative value for delta H, negative value here, minus T, which is the temperature. It has to be in Kelvin. So Kelvin can't have a negative value, right? Temperature cannot have a negative value. It's going to be 0 or greater. So that's always going to be a positive value. And then delta S is positive. And so if this is negative, and then you have minus a positive value and a negative and a positive value here, what's the delta G term always going to be? If this is always negative, and this is always delta S is always positive, what's the overall value going to be there? It's always going to be negative. So here's what you need to remember. If it's got a negative enthalpy and a positive entropy, it's always spontaneous, regardless of temperature. It doesn't tell us how fast the reaction is going to happen. It just says, regardless of temperature, this reaction is spontaneous. So that's what this is saying. Most of you probably can't read that. It says always spontaneous, and they give the example of hydrogen peroxide decomposing. So think about what's going on in this reaction. You got H2O2, hydrogen peroxide. You guys know what hydrogen peroxide is. You've seen 3% solution at the grocery store. It automatically will start fizzing like you pour it on your finger. It starts breaking down and it forms water and oxygen gas giving off. That's why you see the fizzing occurring. Well, hydrogen peroxide has this much energy. Water has this much energy. It's lower in energy. So that is what it's exothermic, rolls down. It's like the ball rolling down the hill. And I'm going from aqueous to a gas being generated, oxygen. So we know that the entropy is greater because we generated a gas. We talked about the last time. If we generate a gas, it's generally a positive change in entropy. So that reaction, when you have an exothermic reaction, it increases in entropy, you'll have a spontaneous reaction. And again, this is what you have to do. You have to look at this equation over and over again and plug in the scenarios. This value is negative for delta H. This value is positive for delta S, an increase in entropy. When you plug in a negative value for delta H and a positive value for delta S, you will always get a negative value for delta G. Always. So that's the easy scenario. That's the easiest scenario possible with this equation. All right. The next one is you have a positive value for delta H. So the enthalpy change is positive. It's an endothermic reaction. It means heat's going into the system. You have a negative value for delta S, the entropy change. So that means it's getting more orderly. It's moving from disorder to more order. So you got a positive value for delta H minus positive value for temperature and a negative value for delta S. Minus a negative is a positive. So you will always get a positive value for delta G. Always. So a positive value for delta G means non-spontaneous. Delta G is greater than 0. Again, we went back and saw that on this slide here, right? Delta G is greater than 0. Non-spontaneous. So that one's easy too. The first two are the easiest ones. Everybody gets those right. Now, the last two is the ones you got to really focus on. You got to keep going through this in your mind till you have it straight in your mind what's going on here. So, here you have an exothermic reaction. Delta H is negative, but delta S is also negative. All right? So delta H is exothermic, but we also have a decrease in disorder. It's getting more orderly. So in this case, it's going to be which one of these terms wins out. If the delta H term wins out, then delta G will be negative. Because if this term is much larger than this term over here, delta H will win out and delta G will be negative because delta H is negative. Now, if this term is small and then we plug in a negative value for delta S here, a negative and a negative makes a positive, we get a delta G that's positive, and that says it's non-spontaneous. So, for this scenario in line number 3, it's temperature dependent. So, here's the example they give. H2O liquid going to H2O solid. So, we're freezing water. Water does not spontaneously freeze at 80 degrees Celsius. Water does not spontaneously freeze at 80 degrees Celsius. Now, we drop the temperature down to -5 degrees Celsius. So at low temperatures, this exothermic part dominates. This term is so small over here that the enthalpy change dominates, and delta G is negative. So, exothermic, yes, when water freezes, it releases heat. That's why we put it in a refrigerator, the freezer, and that's what the refrigerator does. It pumps the heat out of the container, and then it's drawing, the heat flows from the water into the volume of the refrigerator, and then gets taken out by the compression of the gas and expansion of the gas in the refrigerator. But the bottom line is, when water goes from liquid to solid, energy is released. It's an exothermic process. So at low temperatures, the T delta S term does not dominate. The delta H term dominates. Delta G is negative. The reaction is spontaneous. Now here's what you need to remember about that. At 0 degrees Celsius, we saw in our phase diagram for water at 0 degrees Celsius, 1 atmosphere pressure, there's an equilibrium between the solid ice and the liquid water. That was the boundary that you saw in the phase diagram. So at 0 degrees Celsius, the solid ice is in equilibrium with the liquid water. And so when you're at equilibrium, delta G equals 0. So keep that in mind. That at equilibrium, let's go back to the previous slide, delta G equals 0, the system is at equilibrium. So at 0 degrees Celsius, you are at equilibrium between the solid ice and the liquid water. So what I want you to get on the third line for your notes here, spontaneous at low temperatures, non-spontaneous at high temperatures. And you go, what's a low temperature? We're going to figure that out. You have to figure out what that T is. Now, you know for water at 1 atmosphere pressure, it's spontaneous below 0 degrees Celsius. It's non-spontaneous above 0 degrees Celsius. So does 0 degrees Celsius sound like a high temperature to you? Probably not. But that's what it says, non-spontaneous at high temperature. So that's why you got to figure out where that T is. Where is that transition between spontaneous and non-spontaneous? Here's another trick that you got to remember about this one. So you know that when you calculate this out, that the spontaneity between liquid water going to solid ice, the temperature has to be 0, at least 0. What you want to say, it becomes spontaneous at less than 0. At 0, you're at equilibrium. Delta G equals 0. You want delta G to be negative, so it has to be below 0 degrees Celsius for water to spontaneously freeze to ice. All right, last scenario. Last scenario is where delta H is positive. It's an endothermic process. That means heat has to go into the system. But you're also increasing the entropy. Delta S is positive. So it's an endothermic process, but you're increasing the entropy. And I want to know when that reaction becomes spontaneous. So in that case, if delta H is positive, you don't want that term to dominate. Because if that term dominates, then delta G is going to be positive. It's not spontaneous. You want the T delta S term to dominate, because the more positive delta S is, the more overall negative this term is going to be, and that's going to make delta G negative. So for our last case scenario where delta H is positive and delta S is positive, it's spontaneous at high temperatures. Spontaneous at high temperatures, non-spontaneous at low temperatures. And the example they give is mercury 2 oxide goes to mercury liquid plus oxygen. We can see there is an increase in entropy here, because over here you have a solid mercury 2 oxide. Over here on the product side you have oxygen gas given off. So the entropy change is positive. But to break the bond between the mercury and the oxygen requires energy, and it ends up being a endothermic process. You have to heat it up for this to happen. So if it's both positive for delta H and delta S, this only becomes spontaneous at high temperatures. All right, questions on that? Anybody like this totally lost, or are you bored? All right, well, let's look at the next slide. So here's our first questions based off of that diagram, based off this equation right here. All right? So first one is, if a reaction is exothermic and has a positive change in entropy, the reaction will always be what? All right? So you're going to be looking at this equation, And you're going to be answering all three of those equations based on this, knowing that if delta G has got to be less than 0 for this to be spontaneous. Delta G greater than 0, non-spontaneous. Delta G at 0, you're at equilibrium. We got delta H minus T delta S here. And the first question is, if the reaction is exothermic and has a positive change in entropy, the reaction will always be what? So I'll give you a minute on this because some of you probably want to actually try to figure it out, maybe plug some numbers in. Not just, some of you already know it, I agree with that, but some of you need to think about that equation right there. That doesn't help, does it? It's somewhere over here. Oh, that helped a little bit. Yeah, it's not really. All right, 5 seconds. All right, let's see if everybody's bored to death or they're totally lost. Well, it looks like you're bored to death for the first one. 94% it is spontaneous. Delta H is positive. So we got exothermic reaction. This is a negative value. Change in entropy is a positive value, but you got minus a positive. That makes that also negative. And so delta G is going to be negative for question number 1, and it will be spontaneous always. All right, let's do question number 2. If a reaction has a delta H of 10.5 kilojoules per mole, and delta S is 30 joules per Kelvin mole at 25 degrees Celsius, the reaction is, I'm going to give you 2 minutes on this one, because you're going to have to do some calculating. Be careful with the units. What do you think? Why do you think that? There you go. All right. All right, 5 seconds. All right, let's look on the dot cam for this one. So we have delta G equals delta H minus T delta S. All right, so delta H is 10.5. And I would just go on and say 10.5 times 10 to the third joules per mole, because that's what kilo stands for. All right? So 10.5 kilojoules per mole. I want to convert that to joules. And you go, why did you want to do that? Well, when I come over here and say minus the temperature, well, yeah, you're right. It has to be in Kelvin. So 25 degrees Celsius is 298 Kelvin. And then we're going to multiply that by 30 joules per Kelvin mole. And that is what drives it right there, is that Kelvin and that Kelvin have to become unity so that they're both joules per mole, because you can't add or subtract two terms unless they have the same units. All right? So when we calculate that out, let's see, do I have a calculator out here? Now, notice with this one, you don't really have to know the actual value, but you just have to know whether it's going to be delta G's positive or negative. Probably I'll be able to look at that. All right. So you got like 1.06 times 10 to the third? Yes? No? Positive value. All right, so if it's positive, what is it? Non-spontaneous. Let's see how everybody did. 69%. So here, this is what I'm talking about. The first question, most of you got right, because it was qualitative. You just had to say positive or negative. Question 2, you're going to see like that type of problem on the exam, because now we're moving from the theory, the qualitative part, to an actual calculation, and you have to be cognizant of the units. So that kilojoule, and they're not being tricky here. Delta H is generally in kilojoules per mole. Delta S is generally joules per mole Kelvin. And then the math is you can't add or subtract two different units. You can't add or subtract two different terms unless the units are in agreement. So that's why we have to do that. So just be careful. Be methodic. Be careful. That's what we're looking for there. All right. Questions on that one? All right. Let's do the last one here of these three. All right. So if a reaction has a delta H of 1.8 kilojoules per mole and a delta S of negative 113 joules per Kelvin mole, so it's a negative 113, the reaction is. All right? So use the same equation. Figure out your answer. We'll give you 2 minutes on this one. 5 seconds. All right, let's see how everybody did on this one. Non-spontaneous is the correct answer. So you see improvement. So you caught what you're making a mistake on. That's the whole thing about learning is you know that this 1.8 kilojoules has to be 1.8 times 10 to the third joules minus, again, 298 times negative 113 joules per mole Kelvin. That's what it looks like, all right? And then when you get that, you get 35,474 would be a rough answer. All we're looking for is it positive or negative, and it is positive, so it's non-spontaneous. Delta G is positive, so it's non-spontaneous. All right? Questions on that one? All right, let's go on. Now, this is an even more important problem. This is the next step up from those. We did qualitative, we did quantitative. Now, here's the table that we really want to know is, according to table 1, a reaction will be spontaneous only at high temperatures if both delta H and delta S are positive. All right? So what am I meaning by table 1? Well, let's go back. So, this last line, which you, again, probably can't see unless you got your computer, says that if delta H is positive and delta S is positive, the only time that that is spontaneous is at high temperatures. That's what this says as in the process. All right? So that's what we're talking about. They're referring back to this table. That's why you've got to learn the table. You have to know this table. And you're not going to know it tonight, but you're going to memorize this before you get to the test. All right, so according to the table, a reaction will be spontaneous only at high temperatures. Both delta H and delta S are positive. Now, what that is saying, when you hear that, what you want to think about is this. Delta H positive, enthalpy change is positive. If this term dominates, delta G will be positive. If delta S is positive, which means increase in disorder, if this term dominates over delta H, then the term will be negative and delta G will be negative. So that's what they're meaning by at high temperature, this becomes spontaneous. So here we go. For the reaction in which delta H is 199.5 kilojoules per mole, the delta S is 476 joules per Kelvin mole, determine the temperature in degrees Celsius above which this reaction becomes spontaneous. Now, you got to read the question carefully here. This one says, determine the temperature above in which this reaction becomes spontaneous. So they're helping you out. They're telling you that all you have to do is calculate the temperature at equilibrium, and we know above that temperature it's going to be spontaneous. Okay, so they did it a little different. Notice what they did. They take delta S, 476 joules per Kelvin mole, and then they converted that to kilojoules. So they made it 0.476 kilojoules per Kelvin mole because they want to make sure it's going to come up. It's going to be the same units as delta H at the end, right? So you can do that. You can either make delta H in joules or you can make delta S in kilojoules. There's no either way you want to do it there. This example shows converting delta S into kilojoules. All right, so then you look at the next equation and you go, how do they get the first line up here? You're solving for T. All right, so you said, what happened to delta G? Well, delta G, you're at equilibrium. So at delta G at equilibrium, this term is 0. So if this term is 0, you move the delta H over here. That gives you a negative delta H. You divide by negative delta S to get T by itself on this side. So now we have T equals delta H over delta S. You're going to plug in the values for delta H and delta S. Make sure the units are the same, other than the Kelvin, right? Because the Kelvin's what we're solving for. So here's your mathematical thing to remember, is that here you have Kelvin in the quotient of the quotient. That's the same thing as being up in the numerator. And when you calculate this out, you get 419 Kelvin. That is the temperature at equilibrium. Neither spontaneous or non-spontaneous. You're at equilibrium. They didn't ask for the temperature in Kelvin. And if you're doing a multiple choice test, and it asks for it in degrees Celsius, they'll probably have 419 up there for you. But you got to convert that to degrees Celsius. So 419 minus 273 tells us 146 degrees Celsius. Now, that's all the answer you really need to say. 146 degrees Celsius. That's all you have to say for this problem, because this problem says above which the reaction is spontaneous. Determine the temperature above which the reaction is spontaneous. If they don't leave that above in there, then you need to make this statement: at temperatures above 146. At temperatures above 146 degrees Celsius, this reaction becomes spontaneous. Now, one little word makes a big difference: above. Because when you say above, you're conveying to the person, hey, I know what this is. This is when delta H is positive and delta S is positive. And that reaction only becomes spontaneous at higher temperatures. That one word above gives somebody that much information. All right? Questions on that one? It's using this equation. All right, so here's question number 4. Question number 4. If a reaction has a delta H of negative, there is a negative there, negative 1.5 kilojoules per mole, and the delta S is a negative 300 joules per Kelvin mole, so both of these are negative, at 25 degrees Celsius, determine whether the reaction is spontaneous or not. We'll give you 2 minutes on this one. So delta H is a negative 1.5 kilojoules per mole. Delta S is a negative 300 joules per Kelvin mole at 25 degrees Celsius. It's either A, spontaneous, B, non-spontaneous, C, neither, or D, cannot determine. This isn't any harder than the last question. You get one more shot at this. It's 91%. We're looking for better than 91% on this answer. And those of you that already have the answer, you think question 4 is really easy, you guys can start on question 5 so that when I open up the clicker question, you can go, bam, there's the answer. All right, let's see how everybody's doing here. Oh, not as good. 80%. 80% say non-spontaneous. 16% say spontaneous. I'm not getting any bites on cannot be determined. That's good. And then neither. Oh, neither. No, it's going to be one or the other unless it's right at equilibrium. All right? Right at equilibrium. So that means delta G would be 0 when you add this all up. All right, so let's see what we have. So here we have negative 1.5 times 10 to the third joules per mole. Negative 1.5 joules per mole times 10 to the third joules per mole. So I converted my kilojoules to joules. I think that's the easiest thing to do. Minus, we use 25 degrees Celsius because I don't want this to be the determining factor if you don't get it right or wrong. 298 Kelvin. All right? And then we're going to multiply that by negative 300 joules per mole Kelvin. We know we set this up right. Kelvin now cancel out. That's why you have to convert the degrees Celsius to Kelvin because that wouldn't divide out, so it would become unity. So that's why you got to watch your temperature. All right, so now you get your calculator, and you put in 1.5 negative exponential 3 minus 298 times 300 negative equals 87,900 joules per mole. There's no way. Is that right? Is that what you guys are getting? Yes. Anybody getting yes for that? All right. Okay. All right. So is it spontaneous or non-spontaneous? Non-spontaneous. It's a positive value for delta G. Non-spontaneous. All right. We're ready for question number 5 here. So now you know this. You have this information. When, at what temperature does this reaction become spontaneous? At what temperature does this reaction become spontaneous? All right, we'll give you 2 minutes on that one. Do what? Oh, did I make that, did I do that one incorrect? I didn't convert it back, did I? Or did I? Let's see. I have to check it out myself. You guys work it out, and I'll work it out, and let's see if I made a mistake there. All right. You might be right. You might. Let's look at it and see. All right, so let's yeah, those have to be in units of Kelvin, not degrees Celsius, all right? So I'll give you another 30 seconds here. Just change the degrees Celsius to Kelvin. Choose your best answer there. Let's close that one out. All right, let's see what the answers are if they're in Kelvin. below 5 Kelvin. All right, so below 5 Kelvin, and then what was the next choice? D, below negative 5. So you can't have, so let's do this. If this is in Kelvin, it can't be that one, right? You can't have a negative 5 Kelvin. It's either 0 Kelvin or above. So I'll tell you what we'll do. This problem's faulty, but we'll look at, so I'll give everybody credit for this one since the degrees aren't right. But let's go back to this. So you calculated this out and you got 5, right? 5 was your answer? Okay. So then, here's what you want to do. You can either rationalize it out, or you can go back and look at the slide. And we're just going to close that out. When both are negative, the reaction becomes spontaneous at low temperature. So below 5 Kelvin would be your best answer. Below 5 Kelvin. All right? Below 5 Kelvin. Is that what B was? Yeah, so that would be below 5 Kelvin. B would be the right answer. All right? So that was just I will give everybody credit for that since the units are wrong. But it is Kelvin. Below 5 Kelvin would be spontaneous. All right? Questions on that one? So the bottom line is, it's this. It's you assume delta G is 0. That's at equilibrium. You solve for T. T equals delta H divided by T delta S. Make sure the units are the same. This is joules per mole, and that's joules per mole Kelvin. And so the Kelvin being in the quotient of a quotient gives us the temperature in Kelvin. That's not your answer if they just say, when does the reaction become spontaneous? You have to state below 5 Kelvin. Now, if the question has in it, at what temperature below does it become spontaneous or something like that, then all you have to say is 5 Kelvin. But you got to read the question carefully. Sometimes they want you to say below, and that's to reinforce the chart. So just read the question carefully there. All right, Gibbs standard free energy or standard Gibbs free energy. The reason why we have this is because these can be done in tables. You as a student or a scientist can then look at these tables or look on the internet and pull this information off. So the key here is, what does that little standard symbol mean? What does the standard symbol mean here? It means that the reactants are in their standard states and converted to products in their standard states. That's what it means. So what is a standard state? All right, so we've had this before. Yeah, I lost that because I did that. All right, so we've had this before. Gases, if it's a gas, like hydrogen gas, you know what on the periodic table is a gas, like hydrogen, all your noble gases, most of your nonmetals are gases. They have to be at 1 atmosphere pressure. If they're liquids, they have to be pure liquids. If they're solids, they have to be pure solids. If they're elements, they have to be the most stable form at 1 atmosphere and 25 degrees Celsius or 298 Kelvin. So like carbon, the most stable form of carbon at room temperature or 25 degrees Celsius and 1 atmosphere pressure would be carbon graphite, not carbon diamond. All right? And the solutions, if we're dealing with solutions, they have to be in a 1 molar concentration. That means 1 mole of that substance dissolved in a liter of solution. So these are the standard conditions for Gibbs free energy. So we're talking about standard Gibbs free energy. So we've seen this equation over and over again. We saw it with delta H when we did that in Chem 105. It's called the direct method, where it's products minus reactants. We saw this last Thursday with delta S. It's products minus reactants. So here's our general form of the equation. Coefficient A of substance A plus coefficient of B of substance B. These are my reactants. Yields coefficient C of product C and coefficient D of product D. So to find the change, it's always final minus initial. It's always products minus reactants. And these delta G's of formation, standard Gibbs free energy of formations, those are found in a table in the appendix in the back of the book, or if it's the problem, maybe you click on a little hyperlink and it pops that up for you. But those are just like delta H's of formation, standard enthalpies of formation. So we have to have a reference point, so any element in its standard state has a Gibbs free energy formation of 0, just like delta H. And so you're going to take the moles of the product times its standard Gibbs free energy of formation. You're going to add that to the moles of the second product, if you have a second product, times its standard Gibbs free energy of formation. You're going to subtract from that the reactants. The two reactants are A and B. This is the coefficient in front of A. Here's the standard Gibbs free energy of formation of A plus the standard Gibbs free energy of formation of B times its coefficient. Remember, so that you don't make a mistake on this on a quiz or exam, make sure you add up, sum up what's in each of these brackets first before you say this subtracted from the products minus the reactants. If you do that, you won't have that simple, it's terrible to go through all that work and miss it right at the end just because what you ended up doing was saying this plus that minus this, and then you didn't say, you said plus this instead of minus this. So sum up what's in the bracket. That's what this summation sign is for before you subtract products minus reactants. If you do that, you'll be fine. All right, so here it is in action. So here we have carbon graphite. We heat it up in pure oxygen. It forms carbon dioxide gas. So our product is carbon dioxide. We look up in a table the standard Gibbs free energy of formation of carbon dioxide. Subtract from that these two reactants, standard Gibbs free energy of formation of carbon graphite, standard Gibbs free energy of formation of oxygen gas. Well, these two, both reactants, are elements in their standard state. So their Gibbs of free energy of formation are 0 for both graphite and gas. So in the end, the standard Gibbs free energy of change of the reaction is equal to the standard Gibbs free energy of formation of carbon dioxide. So once you looked up the standard Gibbs free energy of formation of carbon dioxide in the appendix, you solved the problem. It's that quick. But you can only solve it that quick if you understand the process. And it's products minus reactants. And the reactants happen to be both elements in their standard states. All right, let's look at another example. Here we have methane gas. We keep seeing methane over and over again. Reacts with oxygen gas to form carbon dioxide and water. Again, this is how, if you're heating your house with a gas furnace or your apartment, that's what it is. All right. You look these up in a table. Here they are for methane, carbon dioxide, water, and magnesium oxide. We're focused on the first three here, right? So these are from a table. Products, carbon dioxide and water, minus the reactants, methane and oxygen. Notice these are multiplied by their coefficients. Let's go back and look at that. There's a coefficient of 2 in front of the oxygen, coefficient of 2 in front of the water. And you say, what happened to the oxygen? Well, remember, oxygen, its standard Gibbs free energy of formation is 0 because that's its standard state at 25 degrees Celsius, diatomic oxygen. That's why its standard Gibbs free energy of formation is 0. So, products minus the reactants, add up what's in this in the products, subtract what's inside the brackets for the reactants. So products minus reactants, we get negative 818 kilojoules per mole. So what does that tell you about this reaction? Is it spontaneous or non-spontaneous? Spontaneous. Delta G less than 0, spontaneous. So yes, methane, when given the opportunity, once we overcome the activation energy, it will burn. All right, I'm not doing the second one. I just want to give you another example. All right, so here is the ultimate problem. Here is the ultimate problem, and this can be a delta G problem or a delta S problem. So we're coming back to this equation here. They're asking you to calculate the delta G. They don't give you the delta H and T and the delta S like we did in the previous problems. They just give you the equation, and they ask, is this reaction spontaneous or non-spontaneous? Okay? So, you know this is the equation that we have to use to calculate Gibbs free energy. And the only difference between this equation and the one you see up there is the one up there is standard conditions, the little not symbol. All right? And the reason why we're using the not symbol on the one that's up here on the slide is that those then are reference to the enthalpy changes and entropy changes that you look in the appendix. So for this particular problem, what you have to do is you have to find the standard enthalpy of formation for your products minus your reactant. So you look those up in a table. Here's my two products minus the reactant. I find that 177.8 kilojoules per mole of energy is required for this standard enthalpy of reaction. It's an endothermic process. It's not a negative value there. It's a positive value, so that tells us it's endothermic. For delta S, you look those up in a table. Again, products minus reactant. Here's where most students make a mistake. Notice the units are joules per Kelvin mole, not kilojoules per mole. These are all going to be in joules per Kelvin mole. So watch your units carefully. Now, we now have solved for delta H naught. We've solved for delta S naught. We plug this into the equation. And naught generally means 25 degrees Celsius, so that's why we know this is 298 Kelvin for temperature. And they converted the delta S into kilojoules. That's fine. In fact, you go, why did they convert it to kilojoules? Because delta G's are in kilojoules per mole generally. Generally, the units for delta G is kilojoules per mole, just like delta H. And so when we calculate this out, we get that delta G is 130.0 kilojoules per mole. Spontaneous or not spontaneous? Not spontaneous at that temperature. Not spontaneous. Doesn't favor the products. Doesn't mean it's not at that temperature, the product is not favored. All right, we could figure out what the temperature is that for it to be spontaneous. We find out that this reaction becomes spontaneous above 835 degrees Celsius. That's when delta G becomes negative, and that's when so we have to heat this up to above 835 degrees Celsius for this to become spontaneous. All right. Yeah, we're running out of time. So then we get into delta G again. We're not finished with delta G, so if you didn't do well on that problem on the last test with delta G, and you didn't do too well on the test before that with delta G, you're going to see delta G again a lot here in chapter 17. So, here's what you need to know. The first one is, let's look at this, and I've actually already, this was from a previous, this was actually before the test, and I just recopied this. So let's go back to here. I've got a 0. I shouldn't have a 0 there first. So what you should have here is delta G, just delta G, is equal to delta G naught plus the RT of ln plus the RT ln of K, which we've done that. All right. Oops. No, I can't do it that way. No, I've got to write this one down because I've already modified that one so much I can see I've got a problem with it. All right. Let me put up the dot cam and we can do it this way. Can I put it on this one? Yeah, all right. Yeah, okay. So the first one, this is what you need to know, and this is what I was trying to get at. Delta G, non-standard conditions, is equal to delta G naught, standard conditions, plus the RT ln of Q. All right? That's what you have to know. Now, what is Q? We've done it over and over. It's the reaction quotient. We are not at equilibrium, and so that's why this is a Q. All right? Now, when you look at the PowerPoint, this is what happens. When delta G is equal to 0, we are at equilibrium. So that's why if you look at the bottom of the slide down here, it says when delta G equals 0, you're at equilibrium. So when delta G equals 0, now you have delta G naught plus the RT ln of K, the equilibrium constant. And then we solve for delta G naught, and we get delta G naught equals negative RT ln of K. All right, you have to know this. You have to know this. Okay? So make sure you've got those memorized, because I just found, I think some people forgot about this on the test, and then you don't have a shot at it. And it's not a hard problem, right? And we saw this problem multiple times. We're going to see it again in 17 here. This is what tells us that this shows the relationship between K, the equilibrium constant. I don't care if it's KSP, KW, KA, KB. It shows the relationship between K and delta G naught. So as K gets larger, this overall term gets more negative, and a negative delta G means spontaneous, right? So that's what we're getting at. So that's why you have to know that one. Now, I'm not going to draw the other one because they do a better job on the PowerPoint. But the other thing you need to know is how do you calculate delta G naught if you're not given delta H and delta S? So, the other equation that you're definitely going to see on the final is this one. Delta G naught equals delta H naught minus T delta S naught. You're going to see that one, and it can be naught or just general, but you're going to have to know that equation too. So, if you're going to find delta G naught, and they don't give you delta H and delta S, or you can't find those, but they give you the delta G's of the standard Gibbs free energy of formations, then you're going to use what's on the PowerPoint. And that is the change in standard Gibbs energy of formation, or the reaction, is equal to the sum. Yeah, that's not very, you can't hardly see it, right? Let's see if I can turn that down just a little bit. Maybe blue's not the best color. Whatever. All right, so delta G naught of the reaction is equal to the summation, number of moles, delta G naught, the formation of the products, minus the summation, number of moles of delta G naught for the reactants. So you need to know that equation too. Make sure you understand how that, and again, those standard Gibbs free energy of formations, you get those from a table. It has to be from a table there. Bottom line is, what you need to know is that if delta G is less than 0, if it's a negative value, then the reaction is spontaneous in the forward direction, non-spontaneous in the reverse direction. You go, why do I need to know that? Well, this chapter we're going to talk about in 17, you're going to talk about galvanic cells or voltaic cells. Those are batteries. Batteries are spontaneous reactions where delta G is negative, and so the electrons come out of your car battery, start up the starter, and then they go back on the other pole of the battery, and we get some work out of those electrons to crank your engine up. Now, when delta G equals 0, your battery's at equilibrium. You're not getting any work out of your battery, and your battery's dead. All right, so that's where we're going with this. If delta G is greater than 0 or positive, then what you're saying is that the forward reaction is non-spontaneous, but the reverse reaction is spontaneous. So that's what's going on with your cell phone. Your cell phone's discharging, gives you energy so you can talk on the phone. And so in that way, it's a spontaneous reaction. But once the battery gets to equilibrium, you go, my cell phone's dead. So what do? You plug it up. And the electrons force the reaction to go in reverse.
And you want a reversible reaction so that you can recharge your cell phone. So that's where we're going in chapter 17 with electrochemistry. All right, so before we're going to talk about oxidation reduction, I want to go back to this slide in Chem 105, and this is so small you can't read it. I can see that now. But let's talk about some rules for oxidation reduction, or oxidation numbers. How about that? So the first rule is this. For oxidation numbers, also called oxidation states, fluorine is always going to be assigned, unless it's just fluorine by itself. Any element by itself has an oxidation number of 0, all right? The electrons are, remember what oxidation number is. It's a way of bookkeeping where the electrons are, who has the electrons, who doesn't. So any element by itself has an oxidation number of 0. So when we're looking at a copper penny, or fluorine gas, or hydrogen gas, its oxidation number is 0. But when fluorine is bonded with anything else, the oxidation number for fluorine will always be -1. All right, so that's the first rule. Fluorine is always -1 for an oxidation state when it's bonded to something else. So when you're looking at these slides and you're listening to the lecture over or something like that, yeah, you'll be able to, hopefully the narrative will help you out here. So rule number 2, these are hierarchical. That means that rule number 1 takes precedence over every other rule. Fluorine being -1 is number 1. Number 1 rule has to be followed. Rule number 2 is that group 1 and group 2 metals, their oxidation states will always be, when bonded with something else, +1 for group 1 and +2 for group 2. Always. All right? That's rule number 2. Rule number 3 is that hydrogen is always +1, always +1, except when it's bonded to a metal. When hydrogen is bonded to a metal, hydrogen will have an oxidation state of -1. So like a sodium hydride, lithium hydride, which is in your cell phone battery. Hydrides are when the oxidation state of hydrogen is -1. All right? Rule number 3 is the hardest rule, and that is oxygen. So oxygen, if I asked you what the oxidation state is for oxygen, you'd probably say -2. And that's a good guess. Generally, oxygen is -2. But when it's bonded with a metal in group 1, oxygen takes on, it could be a -2 or it could be a peroxide. So a peroxide is when you see double 2s. So let's think about hydrogen peroxide. What does it look like? So hydrogen peroxide, sodium peroxide, anything out of group 1, if you see something that looks like this with the double 2s, all right? So you go, I know hydrogen, by rule, has to be a +1 oxidation state. And you've got 2 of them at a +1. You've got 2 oxygen. When you add up the oxidation states for a neutral compound, it has to equal 0. All right? It always has to equal 0 for a neutral compound. Now, had this been a charged ion, it has to equal the charge on the ion. So we have 2 plus 2x equals 0. X equals -1. So each oxygen's a -1. And so you would have oxygen, 2 oxygens together with a -2 oxidation state, and that's a peroxide. All right? There's also a superoxide. It's like each oxygen has a, it's when you have 2 oxygens bonded together with a -1 oxidation state. That's a superoxide. All right? So that's why oxygen is the most difficult. Generally, it is -2, but if you see double 2s, you ought to be thinking peroxide. And then if you see something like potassium bonded to 2 oxygen, then you ought to be thinking superoxide. And then the last rule is that anything out of group 17 or group 7A, fluorine's always -1. Chlorine, bromine, and iodine are almost always -1 unless they're bonded to something that's more electronegative. All right? So if we have something like ClO2, all right, chlorine dioxide. Now, oxygen has an electronegativity of 3.5, and chlorine has an electronegativity of 3.0. And so because oxygen has a higher electronegativity, it gets the oxidation number of -2. And so you have two of those, 2 times a -2. And you have only one chlorine, so we'll put an X in to represent the oxidation number for chlorine. So when we add that together, it's got to equal 0 since this is neutral. And so we get X equals a +4. So the oxidation number for chlorine in this case is a +4. All right? So those are the rules. Make sure you understand them. We've had them before. They were in Chem 105, but maybe it's been a while. But if you don't understand the oxidation rules, you're going to have a difficult time with chapter 17. All right. So here's our clicker questions for today. I want you to be able to look at these compounds in questions 1, 2, 3, and 4 and determine the oxidation number of what they're asking for. So what I want you to do, what I'll do is this. Write these questions down right now on something, and then I'll flip it back to the, well, I don't know if that table is going to help you that much or not. If you're taking good notes, you've got them. I'll put the table up there, but I don't know if you can read it or not. All right? Or you can look it up on Google or whatever you need to do, right? But you got to figure out what the oxidation numbers are. So for the first one, question number 1, we'll give you, I want to see how long it's going to take. So we'll give you 2 minutes on the first one here. I just want to see how long it's going to take for you. And then we'll see, maybe the next one we'll cut it down a little bit in time. So for question number 1, what is the oxidation number for sulfur and sulfur dioxide? And your choices are A is +2, B is -2, C is +4, D is -4. So if you've listened to the lecture, you should be able to get this one. And instead of flipping back to the rules, let's just, there's your rules right there for oxygen. Is that it? Is that 74 all we have today? Anybody else? Last call? All right. And let's see how everybody did. Yep. C is the correct answer, +4. These are -2 each. You got 2 of them, so that's -4 total for the oxygen, so +4 for the sulfur. All right. Let's go a minute and a half on question 2 there. So what is the oxidation number for hydrogen and sodium hydride? And we actually talked about that one in class. So right, make your best guess there. We're up to 76. All right. This one we talked about, sodium it always has to have a positive 1 oxidation state. That's by rule. That rule is above the hydrogen. So hydrogen has to be a -1. This is sodium hydride. When you hear the word hydride, you know that hydrogen is a -1. So let's see, 89%. All right. What was the other choice? C is what some people thought. So if you chose C, you're saying, oh yeah, I know hydrogen ions, and you're thinking H positive. Not here. Not when it's bonded with the metal. The metal takes precedence, and that's why it's -1 for hydrogen. Remember, the reason why that happens, hydrogen, even though it's on the left-hand side of the periodic table, it is a nonmetal. Hydrogen is a nonmetal. And nonmetals tend to gain electrons. All right? Let's just go a minute on question number 3. So question number 3, I want to know what the oxidation number is for carbon in the carbonate ion. All right? And it doesn't say ion, but it's carbonate ion. All right? And at this point, I do expect you to know what the chemical formula for carbonate is. Yeah. Do what? Oh, I've got 2 of the same choices. And is that going to affect the answer? Let me think here. CO3. Yes, it does, doesn't it? I must have had it. We'll still do it, all right? You get to choose what you think the answer should be here. We'll give you a minute on it. I must have been thinking, oh, I've got to get this one in. All right. Let's see how the split is here. Let's see how the randomness between the two. 58 for B, 40 for C. All right. Either one. I'll count both. I'll put them in there. All right. Last one. What is the oxidation number for nitrogen dinitrogen pentoxide? We'll go a minute on that one. There's the formula right there. All right, make your best guess. All right, 5 is the correct answer, 96%. So you say, why did we have these problems? Well, we now know that you can actually calculate your oxidation numbers. So that's not what's going to hang you up in 17. You got your oxidation numbers down, you know the rules. So that's not going to be the problem here. It's going to be something else that throws you off. And that's what we're going to be talking about, the new stuff. So electrochemistry, really important. When we talk about nerve conduction or heartbeat, it's electrochemistry. When we talk about your car battery, it's electrochemistry. and we have to know a little bit about electrochemistry from Chem 107. So we're going to talk about galvanic cells, also called voltaic cells. So either one of those terms are acceptable, galvanic or voltaic. When we hear the word galvanic cells, we're generally thinking something like a battery. If it's spontaneous, we're thinking battery, all right? So spontaneity of the redox reactions under standard state conditions, we're going to look at that, and then the spontaneity of redox reactions other than standard state. Like a car battery, it's not standard state when it's sitting under the hood of your car and it's at 90 degrees outside, or it's 20 degrees outside, or 10 degrees Fahrenheit. That's not standard state conditions, but we've got to know how it works. So electrochemistry, chapter 17. So based off the Lewis structure, that's what gets you through the homework that's due on Friday, homework 16. And then what we're talking about here is for the next homework 17, which is posted, and it's due next week as well. Oh, yeah, the 22nd. You're right, Monday. You're right, Monday, yeah. All right. Yeah, you're right. All right, so let's look at what you need to be able to do. You need to be able to look at a balanced chemical equation and be able to assign oxidation numbers, all right? So according to the rule, when we look at the potassium chlorate there, you know that this is an ionic compound. It's potassium with the ClO3 negative ion. You know potassium's positive 1. By the rules, group 1 has to be positive 1. And then oxygen, by the rules, has to be negative 2. And so 3 times a negative 2 is a negative 6, so that means the chlorine has to be positive 5. So that's important because when you look at the products, potassium chloride and oxygen being formed, you know by the rules potassium has to be positive 1, chlorine's going to be negative 1 because it's an ionic compound. And you know oxygen by itself has an oxidation number of 0. As a pure substance, oxygen has a oxidation number of 0. So you go, okay, I've written out, so what? What am I supposed to get out of this? Well, you're supposed to get out of this reaction that chlorine has been reduced, that it has gained a total of 6 electrons because you went from positive 5 to negative 6. Yeah, now it's 2 chlorines, but you've gone from positive 5 to negative 1, so that's 6 electrons. All right? So for each chlorine, you've gained 6 electrons to get to a negative 1. The oxygen has been oxidized. We've gone from a negative 2 oxidation state to a 0. So that's where we get the word oxidation, right? Oxidized. So oxygen has been oxidized. It's lost 2 electrons. That's why it has as on the product side, it has a oxidation number of 0. So, that's the first type of reaction, okay? The second type of reaction, we look at the second one here. First of all, you should know this is a combustion reaction. You should know that anytime you burn a hydrocarbon and oxygen, you always get carbon dioxide and water. So anytime you have complete combustion with pure oxygen, you always get carbon dioxide and water as your products. So we look over here, and the rule says that hydrogen has to have a positive 1 oxidation state, and that makes carbon have a negative 4. And then oxygen by itself has a 0 oxidation state. Over on the product side, oxygen has a negative 2 oxidation state, and the carbon has gone from a negative 4 to a positive 4. So what I want you to be able to say about this is that, yes, the carbon has been oxidized and the oxygen has been reduced, but also what I want you to be able to do is pick out what is the oxidizing agent and what is the reducing agent. So the oxidizing agent, remember what an agent is? An agent is an assistant. So whatever assists in something being oxidized is the oxidizing agent. So because oxygen by itself gains 2 electrons, it assists the carbon in being oxidized. So the oxygen is reduced, but oxygen is the oxidizing agent. And the mnemonic for that is oil rig, right? So if you remember that, oil rig. And in fact, I was just looking at that. If you Google mnemonics for chemistry, it'll show a Wikipedia page. It's got a bunch of mnemonics on it. And I thought that was pretty neat. So oxidation is loss, reduction is gain. So oxygen, gain electrons, it's the oxidizing agent. Carbon, lost electrons, it is the methane would be the reducing agent. So oxygen, the oxidizing agent, methane, the reducing agent. Make sure you can pick out the oxidizing agent and reducing agent. So we look at this last one, it's even easier. We see that tin goes from tin as an element with a 0 oxidation state to tin 2 positive. It's lost 2 electrons, so tin was oxidized. So tin is the reducing agent. Tin was oxidized, it lost 2 electrons and reduced the copper 2 positive to copper metal. So tin is the oxidizing agent. Tin is the reducing agent and copper is the oxidizing agent. All right, so make sure you can do that. That's important. All right, galvanic cells. So a galvanic cell, the whole reason why we're doing this chapter is we want to talk about how do we get work out of chemical reactions. So the type of work we generally like to get out of chemical reactions is energy, and like a battery, and so, or again, contractions of your fingers or digestion of food, all those are oxidation reduction reactions. And so what we have set up here is we have a piece of copper metal, and it is in a copper 2-ion solution, all right? And then over here we have a piece of zinc metal, and it is in a zinc 2 positive ion solution. So how do you say, how do you know that? Well, copper 2 positive, you guys all know, is a blue colored solution. And you may not remember, but zinc 2 positive is actually a clear solution. So you have an electrode of zinc here, an electrode of copper here. And if you look real carefully, there is a glass tube that is hooked between the two beakers here, and it's called a salt bridge. And the salt bridge allows electrons to flow between the two beakers. And you have to have that, because if you don't allow this to be a complete circuit, then the current cannot flow through the instrument and give you a voltage. So you must, if you had no salt bridge, yeah, you might get a little bit of current at the very beginning when you first drop the electrodes in, but then you're going to get a slightly positive solution, slightly negative solution, and the reaction stops. So you must have a salt bridge between these two reactions in order for this to work. And that's what it does. It transports electrical charge between the two. Notice the blue solution doesn't go over here. The clear solution doesn't go over here. It's not doing that. It's just allowing electrons to flow between the two solutions. And you say, well, what if I didn't have a salt bridge? What if I just poured these two solutions together, put both of these electrodes into the same beaker? Well, the problem with that is the electrons wouldn't want to flow through all this wiring and go out one side and come back, go through this and go through the other side. It would just happen spontaneously within the beaker itself. So you got to keep the two reactions separate. So over here in the clear solution, the zinc solid electrode is being converted to zinc 2 positive. That's all that's happening in this beaker. That's called a half reaction. It's called the oxidation half reaction, because zinc is going from a 0 oxidation state to a positive 2 oxidation state. Over on this side, the blue solution is the copper 2 positive. It's undergoing reduction. It's gaining 2 electrons, and it's actually becoming copper metal. So what you would see over time is this electrode would actually grow in mass. It would get more copper on it, because this copper 2 positive ion in solution would deposit on the copper solid electrode. And over here on this side, you'd actually see this electrode shrink. It would get smaller because the zinc is dissolving into zinc 2 positive. So you'd actually see this electrode go away. This electrode would get larger in mass. All right? So zinc is being oxidized, copper 2 positive being reduced. And the voltage is the potential energy between these two reactions. That's what voltage is. It's potential energy. So between the zinc being oxidized and the copper 2 positive being reduced, we have a voltage of 1.10 volts. All right? And it doesn't matter. Here's another thing about voltage. It doesn't matter how much solution you have here. I could have a gallon of this and a gallon of that, and the voltage would still be the same. So voltage, this is important. I saw that as one of the learning objectives. Voltage is an intensive property, which means it's amount independent. Just like density, it's amount independent. If you've got two, it doesn't matter whether you have two little beakers of these solutions or you have 2 gallons of these solutions, you're still going to get a voltage of 1.10. All right. If the reaction is spontaneous, that means this reaction happens on its own. We know what spontaneity is. It means delta G is negative, right? If it's spontaneous, we call it a galvanic cell. Some people call it voltaic, galvanic or voltaic cell. All right. Now, this is the next thing, and I put these in color because these are very important, the words, the terminology. Anode is where, in a galvanic cell, that's what we got to start with first. In a galvanic cell, a battery, the anode is where the oxidation takes place. So if you look at your car battery, you will see a negative symbol on the red end. It's got where the red cap attaches to the battery. That is the anode. That's where the oxidation happens, and the electrons leave that, and they go through the starter, and then they go back to the other side. So the anode is where oxidation occurs. That's where the zinc loses its 2 electrons. It becomes zinc 2 positive, and now the electrons go wherever. We get some work out of them. They go back onto the other side, which is called the cathode. And the cathode is where the copper 2 positive ion solution is reduced back to copper. So cathode is reduction, anode is oxidation. And the zinc, let's go back, and the zinc, again, this is called a half cell or a half reaction, and this is a half cell, the copper solution. So these are 2 half cells. Or if we break this out as zinc going to zinc 2 positive, that's a half reaction, and then copper 2 positive going to copper solid, that's a half reaction. All right, you must have a salt bridge. Make sure you know about the salt bridge. That's a common question on an exam, or they want to make sure that you understand you have to have some way for the electrons to get through those half cells. There's got to be a connection between them, and that is a salt bridge. And again, it just allows the electrons to flow. It's not like the copper 2 positive solution is going over to the other side. That's not what's happening. It's just allowing charges to flow. Generally, the salt bridge is made of some other substance like potassium chloride. You actually take a piece of glass tubing, fill it full of 1 molar potassium chloride, put a couple of pieces of cotton on the end of it so it doesn't flow out. It allows the electrons to flow, but it doesn't allow the substances to mix. All right, so we're going to look at cell potential. That is the difference between these 2 half reactions that generates a potential energy, which we call cell potential. Now, you have to be able to interpret, and you're going to be tested on this, you have to be able to interpret this symbol, what this means. So by convention, over on the left-hand side, that is where the anode is. So you always start with the anode. So in this case, the anode is zinc. This represents a barrier. And then that's the solution inside that half reaction or half cell, and that's the zinc 2 positive solution. You should actually say what the concentration of that zinc solution is. The zinc ion, in this case, it's 1 molar. The double lines here represent the salt bridge, all right? That's the actual break between the 2 half reactions. This represents the salt bridge. Then you have, in the other half cell, the copper 2 positive blue solution and the concentration of that solution. And then we have the barrier between the solution and the electrode, the copper electrode. The copper electrode is where the cathode is. So anode on the left and cathode on the right. Anode is where the oxidation occurs, and reduction of the copper 2 positive to copper happens at the cathode on the right. All right, standard reduction potentials. Now, we're going to spend a lot of time with this. We're not going to have enough time to develop it completely here, but I want to give you a taste of this, so if you're working over this on the weekend, you've got an idea of what's going on. So energy, remember we've talked about energy. I cannot tell you how much energy is in this pen. I cannot tell you how much energy is in here unless I destroy it, unless I set it on fire or something like do a chemical reaction on the pen. I do not know the absolute energy in this pen. So all I can measure is changes in energy. So remember when we talked about delta H, we said enthalpy, which is heat, we cannot determine the amount of heat in this pen unless we undergo a chemical reaction. So we said we got to have an arbitrary, we have to have a point to define as 0 H, 0 enthalpy. And the rule is if it's an element in its standard state, the enthalpy is 0. So that's why we have standard enthalpies of formation of any element on the periodic table has an enthalpy of 0, enthalpy. So here is how we establish 0 cell potential, or 0 energy for the cell. This is the simplest of electrodes that we can make, and it's called the standard hydrogen electrode, SHE, standard hydrogen electrode. We have 1 molar hydrochloric acid. We have an inverted glass tube. We pump hydrogen gas at 1 atmosphere into the tube, and we have a platinum electrode here. So what happens here is the hydrogen is reduced, the hydrogen ion is reduced by gaining 2 electrons and forms hydrogen gas, and so you can see the gas bubbling off of the platinum electrode. We assign that particular energy 0. That electrical potential is 0. We assign it a 0. Even though it's not really 0, that's our reference point, just like sea level. So then we attach that reference electrode to our zinc solution that we just saw in the half reaction. So here's our zinc anode. Here's our zinc 2 positive solution, 1 molar. So we assume any voltage difference between the reference electrode, the standard hydrogen electrode, and the zinc, we attribute that only to the zinc. So now zinc has been assigned that the oxidation of zinc to zinc 2 positive compared with this reference electrode has a voltage of 0.76. So any voltage read here, we assign it to the solution opposite the hydrogen electrode. So then we do the same thing for the other half reaction. We had a copper 2 positive solution. We had a copper electrode. We set that equal with the, we set that in connection with the standard hydrogen electrode. Notice we have a salt bridge that allows the electrons to flow. And the potential energy is 0.34. So any potential energy here is assigned strictly to the copper. All right? And so based on that, we can now determine the total energy between the zinc solution and the copper solution. So let's see if that's on the next slide, and if it is, we'll finish there. All right? So here it is. This is what you got to look at. First of all, notation. Zinc, solid, that's the anode with the zinc 2 positive solution. There's the concentration. There's the salt bridge. There's the hydrogen ion. The hydrogen ion is being reduced to hydrogen, and there's my cathode. This is the reaction that's happening at the anode. That's oxidation. This is the reaction that's happening at the cathode. That's reduction. When we add these two reactions together, before you can add them together, whatever number of electrons is lost here has to be exactly the same number of electrons gained here. Had this been a 1 here, you would have had to multiply the entire equation by 2. But these electrons have to cancel out when you add the 2 half reactions together. So when we add these 2 together, we get this equation. Here's what you need to know for your homework. The standard cell potential is equal to the standard cathode cell minus energy minus the standard anode. It's always cathode minus anode. Cathode minus anode. So when we subtract these 2, and we know this one is 0, it's 0.76 volts for just the zinc. All right, so this is, we said this one's 0 for the standard hydrogen. That's our reference point. That's what it is for the zinc. We do the same thing for the copper. Well, we have to skip that one. All right, we'll stop right there today. We'll stop right there. But that's what you need is that equation to do some of your homework on chapter 17 there.